So hello everyone, this is Ahmed Ibrahim, and today I am going to discuss with you my presentation on intelligent reflecting surfaces. So the outline of this talk will be as follows. First, I will discuss the main fundamental of the surface. After that, the use cases and application of these surfaces in wireless communication. And I will end up with challenges that we may face while deploying this surface in real communication system. So simply, this surface is a two-dimensional surfaces that composed of many reflecting elements. This reflecting element is simply small antennas, such as microstrip patches antenna. And small by small, I mean that the length and width of this reflecting element are sub-wavelengths, typically between lambda/2 and lambda/10. And the idea is that each reflecting element in this surface is connected to a tunable chip. And the main function of this tunable chip is to control its load impedance. And given that you're going to control the load impedance per each element individually, so at this moment you can control the induced phase shift per each element individually. Typically, the type of tunable chip used are binary or varactor. So imagine that we have a reflecting element that is connected to a pin diode, and pin diode have two states, on and off state. We'll find that on on state we have a load impedance that is short circuit, and in off state we have a load impedance that's open circuit. And this will result in inducing phase shift difference between on and off state that is pi. So we may have in on state a phase shift per each element that is 0, and for off state a phase shift per each element that's pi. And given that you can control all the elements individually, by this idea you can, for example, design your phase shifts of each element such that the scattered wave added constructively at certain point or destructively at another point. So imagine that you want to change or induce a continuous phase shift. So you may decide to replace the pin diode with a varactor. At this moment, you can have a load impedance that varies from short circuit to open circuit, and this will result in a phase shift that varies from 0 to 2 pi per each element. In addition, if you decide to attach per each reflecting element a variable resistor, at this moment you can control also the amplitude of the reflection coefficient. So you can control for each element the reflection coefficient in terms of amplitude and phase of each element. The structure of the IRS will be something like this. First, you have the array of antenna. After that, you may have copper port that will act simply as a shielding port or to prevent leakage of the wave on the other side. And after that, you may have a control circuit board that composed of the tunable chip and such as pin diode, variable resistor, stuff like this. And you have the brain of the IRS, which is a microprocessor or a controller, something like Arduino kit. That to choose the states of the pin diode and simply to control the reflection coefficient of each element. So what's different between intelligent reflecting surface and normal surface, such as metal plate, is that in case of a normal surface, we follow specular reflection, which is a reflection that occur when light incident or reflect on a mirror, that the angle of incident and the angle of reflection are equal. However, and this follows Snell law. However, in case of intelligent reflecting surface, we follow a different reflection model. We follow anomalous reflection, that the angle of incident and the angle of reflection don't have to be equal. And these come from the idea that you can alternate the surface impedance or the impedance of each element. So you can control the phase shift induced for each scattered wave in each element. So you can constructively combine all scattered wave at certain direction. So you can change the angle of incidence or the angle of reflection and be different than the angle of incidence. And this follow generalized the Snell law that the angle of incidence doesn't have to be equal to the angle of reflection. Moreover, IRS has and its element has widely named as meta surface and meta atom, where meta is a Greek word that meaning beyond, and this represents the beyond normal operation of this surface in terms of anomalous reflection. In addition, you may find in the literature many other names of for the same thing, intelligent reflecting surface, such as large intelligent surface, large intelligent meta surface, reconfigurable meta surface, reconfigurable intelligent surface, and so on. There are two modes of operation for this intelligent reflecting surface. The first one is active mode, where the surface or this surface is connected to RF chain or chains, power amplifier, and DSP has DSP function. And this represents the next step beyond massive MIMO, like holographic MIMO or holographic beamforming. And there is no big difference between this and massive MIMO, except that the surface or the number of elements get extremely large, 1,000 and more. The other mode of operation is passive IRS, where the intelligent surface doesn't have any RF chain or power amplifier or DSP function, and it doesn't consume any power for transmission. That's why it's named passive. However, of course, it consumes minimum power for controlling and tuning the element. So it's better to name it nearly passive. So yeah. Also, we can see this IRS as a full duplex multi-antenna amplifier forward relay. However, what is the difference between IRS and the relay is that the IRS is nearly passive element, doesn't consume any power for transmission, but only for control. But of course, relay is active element. In addition, it's a full duplex, but there is no self-interference induced by the surface to achieve this full duplexity. Moreover, it doesn't induce any thermal noise to the forward signal, which usually occur in the amplifier and forward relay. The important thing about this intelligent reflecting surface that is changed our viewpoint to the whole communication system, like from first generation to fifth generation. We always look at the wireless environment or wireless channel as it's something fixed by nature, and it's true. And our method is to design sophisticated technique as a transmitter and as a receiver in order to compensate the wireless channel effect. However, using IRS, you now are capable of shaping the wave between the transmitter and the receiver. And in some sense, you now have the ability to control the wireless channel itself. And this is like make IRS make the wireless channel itself as a new player or a new optimization variable that you should jointly optimize with the transmitter and receiver. And here comes the idea of smart radio environment, that the environment or the wireless channel is generated by nature. However, you can control it by design or more precisely by using this surface. And most of application using this surface depend on this idea that they are trying to solve certain drawback in the wireless channel by controlling it. So if we start discussing the application of the use cases, we find one possible application for this intelligent reflecting surfaces like coverage enhancement. Like now we have user A that feels blockage for its received signal from base station because of the shadowing or the blockage from P1. However, if you deployed some surface on P2 and P3, you can create somehow virtual link, and you can improve the SNR, improve the coverage of this system, which may be useful especially for millimeter wave communication, which are highly affected by blockage. Another use case that you can deploy this IRS to improve the SNR as a cell edge user, where cell edge users suffer from both a high signal attenuation from its serving cell and also high interfering power from the nearby cell. So given that you are going to deploy some surfaces at the cell edge, you have the opportunity to, for instance, design the phase shift or the reflection coefficient of the element in the surface, such that the desired signal is constructively added at the user, and the interfering signal is destructively combined at the cell edge user. Another use case of this service is that it can assist in non-orthogonal multiple access, where conventional orthogonal multiple access means to serve single user per orthogonal channel. And non-orthogonal multiple access means to serve multiple user per one orthogonal channel. And if we speak about NOMA with MIMO, so it means to serve multiple user on the same spatial direction, which represent the orthogonal channel in this situation. However, non-orthogonal multiple access with MIMO is not always preferable. If the user channel vector that shares the same spatial direction are orthogonal, it's better to use orthogonal multiple access. If the user channel vector are aligned, so it's better at this moment to use NOMA with MIMO. So some researchers suggest to use distributed intelligent reflecting surface such that they control the channel vector of user 1 dash to make it aligned to user 1 and combine these two user 1 and user 1 dash in one spatial direction. And same for IRS2 to align channel vector for user 2 and user 2 dash to make NOMA with MIMO more efficient in terms of spectral efficiency. Another technique that can be used with IRS is the IRS itself can be used to perform index modulation. Or index modulation means that the data bits are encoded in both the modulation scheme that you are going to use and the antenna index. And by this way, you can improve the bits per channel use from log to M, if we are speaking about a SISO system, to log to M plus log to NT, while maintaining like single RF chain, very simple transmitter. However, you could, by just doing index modulation and just take account of modulating data over the antenna index to improve the spectral efficiency. In the same analogy, you can use intelligent reflecting surface to perform index modulation. You can divide this the element of the surface into group and give each group index. And instead of coding the data bit in terms of the modulation scheme and the antenna index, we are going to encode the data bit in terms of the modulation scheme and the index of the group of element in the intelligent reflecting surface. So if you are going to, for example, to encode in terms of index 2, you are going to switch on all the reflecting element in group 2 and switch off all the other elements in other group. And by switch on and on, I mean off and on, I mean that you set the amplitude reflection coefficient of this element equal 1 or 0. And of course, you have to choose or to design the optimal phase shift per each element. So you can also perform index modulation, but instead of using multi-antenna, using IRS. And at this moment, your bits per channel use will go from log to M in SISO to log to M plus log to N. Also, IRS can be used to assist massive device-to-device communication, where the IRS can act as a reflection hub that try and the element of IRS are designed and the phases are chosen such that the desired signal are constructively added at the intended user and destructively added at the unintended user. Also, IRS can be used for wireless power transfer, where wireless power transfer target the transmission of electrical energy without using wires and cables. And the main idea is that the receiver uses rectangle and while it receives the wave, it tries to extract and charge its load using the receiving wave. So by using IRS, you can like focus the wave toward a certain user such that it can extract energy from it. And this could be like potential in terms of Internet of Things network. Moreover, IRS can be used for channel rank enhancement, wherein point-to-point MIMO, the channel type itself or the propagation of channel play an important role. If we have a rich scattering environment, we have a 4-ranked channel matrix, and we can deploy spatial multiplexing by sending independent data stream. And this is why they named as spatial multiplexing gain. However, if the channel changed from, or the environment changed from rich scattering to line of sight environment, at this moment, the point-to-point MIMO channel matrix become rank efficient, or more precisely, become rank 1 channel. So at this moment, you lose this spatial multiplexing gain, and the effect of MIMO system, or the benefits of point-to-point MIMO system, become merely an array gain. So in order to restore the spatial multiplexing pack in case of line of sight environment, you can deploy like distributed intelligent reflecting surface in your environment, in your line of sight environment, and change your environment from line of sight into like artificial multipath propagation environment. And by this, you gonna to increase the rank of the channel matrix, and you restore the spatial multiplexing gain back. So this was some of the application on intelligent reflecting surface. Now we are going to discuss the main challenges that we may face while using these surfaces. I believe that the most important challenge is the channel estimation of a communication system that deploy an intelligent reflecting surface. So the performance of a communication system assisted by intelligent reflecting surface is guaranteed or depend on the accurate tuning of the reflection coefficient of each element in this surface. And this, of course, like will depend on the accurate channel estimation. And by deploying this surface, we have like 3 types of channel. We have already direct link channel, from example, base station to user. We have another channel from user to IRS, and we have another channel from IRS to base station. So number of variables to be estimated are increased. This is number 1. In addition, the most selling point of this IRS that's nearly passive, that you don't pay anything for transmission, but of course you pay powerful control. So given that the IRS is passive, doesn't have any capability to transmit pilot, receive pilot, or processing signal. So IRS itself, we can't rely on it to estimate the channel, but we have to do all the channel estimation at the base station. So the benchmark idea for channel estimation, just to understand the problem, is training-based channel estimation. So it can be like divided in 2 stages. We would like to estimate H0, H1, and H2. So initially, I will turn off all the elements in IRS and user send 1 pilot, so estimate H0. And after that, I will turn off only 1 element in the IRS and send uplink pilot, so estimate the product between element in H2 and particular element in H1. And then I iteratively do the same step, like turning on 1 element while other are off, and estimating all or the product between H1 and H2. So imagine that like if we are going to use training-based channel estimation, we'll have like very long overhead that may make this surface not practical. However, some researchers suggest to like because most probably the channel between the base station and the IRS will be sparse, to use compressive sensing technique for channel estimation. This may shorten the little bit the training you need, but it will not vanish and still a lot of overhead. Another researcher suggests to have some active element in the IRS to help in transmitting and receiving pilot and estimate the channel at IRS itself. But still, break the most selling point of IRS that's totally passive. Another drawback that I believe that is very important is that it has very unfavorable past loss model because we have like two hop channel, first hop from base station to surface and second from surface to user. The first hop channel, the past loss of this first hop will be relative to R1 square, and the second hop will be relative to R2 square, where R1 and 2 are the distances. So, and the overall effect of the overall past loss will be relative to R1 multiplied by R2 all square. And this like very unfavorable past loss model because it's multiplication of distance, so it has very bad drawback. However, what's a good point that you can coherently add all the scattered weights, such that you have in the SMR an n square gain. So it's like a trade-off between number of element distances. But this is the most, from my opinion, challenges. So this is my presentation. Please ask me if you have any questions.